Hello and welcome to the presentation of our project, Tipping AFL Matches with Bayesian Multiple Linear Regression. I am Joshua Elliott and I was joined on this project by Shayan Ahmed. The goal of our project was to use Bayesian methods to create a model of multiple linear regression to predict the margins of AFL matches. This is a problem which has been tackled using a variety of different methods, and in our project we look to see how the performance of a Bayesian approach compares to other methods. We compare the performance of our model to a classical multiple linear regression model and AFL predictions created by other models. A point of difference in the Bayesian approach is the ability to generate posterior distributions for match predictions, which we will also demonstrate. Our dataset is comprised of more than 2,000 observations of 5 variables. We have one observation for each AFL match played between 2010 and 2019, and we will use the model to make predictions on the matches played in 2020. The dependent variable y represents the margin result in AFL games from the perspective of the home side. If the margin is positive, it means the home side won. If it is negative, it means the away side won. If it is 0, then it means the match was a draw. The histogram of the dependent variable shows that the margin is a normally distributed variable. The independent variables x1 and x2 record for the home and away teams respectively whether or not the match was played in their home state. If it was, then these variables take the value of 1. If not, they take the value of 0. The distribution of these variables can be seen in their scatter plots. The x3 variable attempts to provide a quantitative comparison of the recent form of the players named in the home and away sides. It tracks the differential between votes received in the AFL Coaches Association MVP award in the last year for the players in the home side compared to the players in the away side. The scatter plot for this variable shows that it is positively correlated with margin. As this variable increases, so too does the likelihood of a positive margin, and vice versa. The x4 variable records the differential between the home team's playing experience and the away team's playing experience. For example, if the players named for the home team have previously played a combined 2,000 AFL games, and the players named for the away team have played 1,500, this variable will read 500. Like x3, this variable is positively correlated with margin. The x3 and x4 variables do share some correlation, but not enough to cause multiple collinearity issues. This slide shows our JAGS model diagram and the code that was used to specify this model in R. Normal distributions are used as the priors for the intercept and the slopes because these values could lie anywhere in the domain of negative infinity to positive infinity. A uniform prior distribution was used for variance. A normal distribution is used for the likelihood because, as we previously observed, the dependent variable margin is normally distributed. The JAGS code shows the values of the prior distributions that were specified. We did not have any expert information for these priors, and so specified non-informative priors, as can be seen on this slide. We also tried running the model using the parameters as determined by a classical multiple linear regression model as the priors for the Bayesian approach, but found that this did not result in a significant change to the outputs. For this reason, we used the non-informative priors seen here. Diagnostic checking was conducted to ensure representativeness and accuracy in the model parameter prior distributions. As the charts for beta 0 show, the chains have converged, the shrink factor is below 1.2, the densities overlap, there is no autocorrelation, the effective sample size is greater than 10,000, and the Monte Carlo standard error is close to 0. These conditions were satisfied for all of our posterior distributions. To improve the diagnostics and the efficiency of the simulation, we centered the data in the independent variables before running the JAGS model. This slide shows the posterior distributions for the model parameters that were created by our analysis, covering the intercept, the slopes for the 4 independent variables, and the variance. The slope for x1, home, has a highest density interval between negative 6.3 and 7.16, so it is unclear whether this variable has a positive or negative relationship with the dependent variable margin. However, all of the remaining variables possess a clear relationship to the dependent variable. We can see that the mode reported for x2, away, is negative but equal in absolute value to the mode reported for the intercept. This suggests that the home team generally possesses an advantage, but that this is negated if the away team is also in their home state, which appears to be a logical conclusion. Both x3, the votes differential, and x4, the experience differential, possess positive relationships to the dependent variable, which we would expect given that they appear to do so on the previously shown scatter plots. This slide shows a comparison of the observed data in the original dataset, shown in red, to a distribution of values predicted using the model parameter modes reported in the previous slide. We can see that while there is a reasonable amount of overlap, the distribution of predictions is much more compact than the observed values. This is a broad trend across AFL margin prediction models. We have observed that these models rarely ever predict big margins, even though big margins can occur. While we know that big margins are often observed in AFL games, predicting which games they will occur in remains a problem that it has not yet been possible to provide a solution to. We use the mode parameter estimates created by our analysis to predict the result of every match of the 2020 AFL season. Predictions were adjusted for the shortened length of quarters in 2020, which occurred due to the impact of COVID-19. The model was able to successfully tip 108 of the 153 matches in the home and away season, a success rate of more than 70%. We also calculated a mean absolute error of the predicted margin compared to the observed margin at 23.2 points. These results are essentially equivalent to the results produced by other AFL tipping models. As such, we can conclude that a Bayesian approach to this problem is equally as effective as other approaches. In addition to that, the Bayesian approach can be used to create posterior distributions of match predictions, providing more information about match predictions than would be seen with a classical multiple linear regression model. This slide shows posterior predictions that were created for the first week of the 2020 AFL finals, which have again been adjusted for the shortened game time.